Hey everybody, it's Coach Stoltenberg again. Starting the next unit. This unit is called Thermochemistry, and we're basically dealing with energy. It's the unit in chemistry that we talk about energy the most. Thermo might make you think about like thermometer or temperature or heat, and we'll talk about heat in this. But really, what thermochemistry is all about, it's about energy. So we're going to start by looking at different kinds of energy and kind of try to figure out where this energy is coming from, and then we're going to look at ways it gets transferred, and the difference between heat and temperature, and then ultimately we'll get to something called specific heat, and we'll actually get to do some math. I know you guys are missing it because, gosh, it's been so long since we got to do math. Yeah, we'll have an equation, specific heat equation, relatively simple, but some of the units are new, so it might be slightly confusing to begin with. But we'll get to that in the second part. This part of the video is basically just an introduction to thermochemistry and energy and all the fun stuff that goes along with that. So let's jump right into it. Here we go. All right, here's your textbook definition. Energy. Energy is the capacity to do work. It can take many forms. We're going to look at a bunch of different types of energy here in a little bit. But energy is what allows anything to work. What type of energy you're using to accomplish that work might change from one job to the next, but energy is what allows us to do that. Okay, so what kind of energies do we have here? Well, we're going to start with two that are pretty straightforward and you probably are familiar with. These are more physics terms than it is chemistry, but when you start talking about energy, that's where physics and chemistry kind of start to blend together. Potential energy is energy, stored energy, energy that's not being used, also known as energy of position. Something that has potential energy is not currently using it, but has the potential to be able to use it. In physics, when we say energy of position, in physics it's talking about how high it is above the ground or how far it has to fall. An object that's on the lowest shelf of a bookcase would have less potential energy than an object that would be on the highest shelf of a bookcase. That's definitely more of a physics thing than it is chemistry. But potential energy should be a term you're familiar with. The opposite of potential energy, kinetic energy. That's taking that potential energy and putting it into motion. Kinetic energy is the energy of motion, or the energy associated with movement. A ball sitting on top of a hill, not moving, has potential energy. You kick that ball down the hill, now it's rolling. Now that potential energy is being converted into kinetic energy. Energy of motion. Again, kind of more of a physics term than it is a chemistry term, but we'll come back to that actually here in a second. Chemical energy. Now we're talking about chemistry stuff because there's the word chemical. Chemical energy is the energy stored within the bonds of chemical substances. This is the energy that we get when bonds are broken, or the energy that we get from breaking down stuff like food. This is the energy that's stored within chemical bonds. When you break a bond, that usually comes with the release of energy, and that's what that chemical energy is. Notice it's energy stored, meaning it's not being used currently. Guess what else is stored? That's right, potential energy. Chemical energy is a form of potential energy. Potential energy, chemical energy is potential energy. Okay, what's next? Nuclear energy. Oh, this is definitely a chemical concept. Nuclear energy is the energy associated with the nucleus. It's the energy stored within the collection of neutrons and protons. We're not going to get to nuclear chemistry till the end of the year, but that is coming up pretty soon. Nuclear energy is a really fun topic to talk about. but it's the energy that's stored in that nucleus. So way we get that out is by, well, currently it's by splitting a nucleus, and when that nucleus splits, it releases a lot of energy, a whole lot of energy. Again, though, it's energy stored, so nuclear energy is again a form of potential energy. Chemical energy is the energy stored within the bonds between two atoms or more. Nuclear energy is the energy stored within the nucleus of an atom itself. Alright, what's next here? Electrical energy. This is the energy associated with the flow of electrons. We know about electricity, we use it every day. It's actually a stream of moving electrons. And notice flow, moving, the movement of electrons. We know electrical energy then is a form of kinetic energy. Electric energy is more of a physics thing. We don't deal with electricity a whole lot in chemistry, but when you get to physics, your first year of college, second semester physics, be prepared, because they're going to start hitting you with all kinds of electrical calculations and stuff, and it's lots of fun. Alright, all those are nice, but here's the one that we're going to be concerned about the most, and kind of the focus of this unit, and that's thermal energy. Thermal energy, and I love this definition. It's one of my all-time favorite definitions. Thermal energy is an outward manifestation of movement at the atomic level. The outward manifestation of movement at the atomic level. That's quite a definition there. Very fancy. So let's kind of think about it. What does that actually mean? Thermal energy. Well, one, we know it's from movement. So we can think of thermal energy as kinetic energy. Well, it says movement at the atomic level. So what we're talking about here is movement of atoms. So this is the energy that's produced by the movement of atoms. Now, if I was standing up in front of class, I would be demonstrating this for you, but I think you can still get it without having to see me do it. So I want you to take your hands, and I want you to put them palm to palm, and then I want you to start sliding them back and forth, palm to palm. What starts to happen in between your hands? What starts to happen to the surface of your skin in between your hands? It starts to warm up, right? It starts to get warm. When you stop, the palm of your hand, it's a lot warmer. And the faster you move those hands, the hotter it's going to get, right? Well, why does it do that? Why does your hand start producing heat? Anybody? It starts with an F. It's called friction. Friction. The resistance of two objects sliding past each other produces frictional heat, right? And this is something that we're relatively familiar with. It's not that complicated of a concept. Well, if you're trying to understand thermal energy, kind of think of it like that. You have billions of atoms next to each other that are moving, right? And those atoms are constantly moving, constantly vibrating, and that movement of atoms being next to each other is kind of like your two hands rubbing against each other, and that's where that energy, that thermal energy, comes from. When we talked about movement of atoms earlier in the year, we talked about how all atoms move at the atomic level. Even the solidest of the solidest of the solids still has movement at the atomic level. There's no such thing as no movement at the atomic level. Well, it's theoretical, but as far as we know, it's not possible to be reached. So that should tell you that all things have some value of thermal energy, because there's always movement at the atomic level. So even going to the North Pole and finding the coldest piece of ice that you can find, that ice still has some value of thermal energy, because its atoms are still moving. No matter how cold it is, the atoms are still moving. Either way, thermal energy, that's what we're focusing on. So There you go. Again, movement of atoms at the atomic level. Thus, it's a form of kinetic energy. All right, next. All right, talking about temperature and thermal energy and how they're not the same thing. A lot of times people confuse temperature with thermal energy. Temperature is just a measure of thermal energy. It's actually the average of whatever body that the average thermal energy of whatever body you're measuring the temperature of. They're not the same though. They're not equal. One thing that the biggest difference between temperature and thermal energy is that mass is a huge factor when it comes to thermal energy. And you'll see that when we get to the specific heat equation. Mass is factored in every single time. It contributes quite a bit. So a little example here. We'll compare a steaming hot cup of coffee to a lukewarm bathtub full of water. Well, while this one's way hotter, right? 90 degrees Celsius, nearly boiling. 40 degrees Celsius, a little bit above room temperature. This one's temperature is way, way higher, but this one is going to have a much higher thermal energy because the mass of all the water in this bathtub is so much greater than the mass of whatever liquid's in this coffee cup that ultimately the more thermal energy would be here than here. Now, if you increase this to the volume or to the mass of this, then yes, this would have the greater thermal energy. But since there's so much more mass here, this would be considered to have the more thermal energy. So remember that mass factors in very significantly into the value of thermal energy. The more mass you have, the greater the thermal energy. All right, let's talk about heat. What is heat? Because there's another thing that people kind of interchange. They say thermal energy is heat. Well, it's kind of true, but you have to be a little bit more specific. Heat is the transfer of thermal energy. Heat is what is a form of thermal energy, but specifically when it's being transferred between two bodies. And here's a very important thing. These two bodies have to be at different temperatures. If they're not at different temperatures, that's what we call thermal equilibrium, and heat doesn't exist because they're at equilibrium. There's no difference, so there's no transfer of heat in one direction or the other, from one object to the other, is how I should say it. So there has to be a difference in temperatures. Then the heat transfer is actually automatic. Thermal equilibrium is something that happens automatically. Like it's a process that happens without any other influence. It happens automatically, and it's something that we actually are constantly trying to combat or to fight. On really, really cold days, to keep us from getting cold, we put on lots of clothes. We're trying to prevent thermal equilibrium. We're trying to keep our body heat in our bodies and not let it equal the heat, or not let the heat transfer get to where it's equaled out. That would mean we'd be really cold. Or in really hot days, we try to keep our houses really cool. Try to fight that thermal equilibrium so we don't get super hot. It's something that happens automatically. There's nothing we can do about it. But the only way it happens is if there's a difference. Okay, so when we're talking about his heat transfer, it's very, 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 very specific transfer. And it only happens in one direction. It always flows from warmer to cooler objects. It is impossible for it to go the other way. Heat only flows from warmer to cooler objects. So here, you got an example in the picture, a guy holding a hot coffee mug. The coffee mug will have more thermal energy than his hand. So that person is going to feel the heat of that mug transfer into his hand because his hand is a lower thermal energy, and the heat energy will transfer from the cup to the hand. In the second picture, he's holding an ice cube. Now when we use ice, we say we're going to cool something off with ice. We're going to make it colder by putting ice in. We take a glass of tea, we add ice, and we're cooling it down. Well, technically, that's kind of wrong to say, because the ice is not cooling the liquid down, and in this case, it's not cooling the hand down. What the hand is doing, or what the tea is doing, is actually warming the ice up. It's transferring some of its thermal energy into that ice cube to try to reach thermal equilibrium, and as a result of that process, it loses some of its thermal energy and starts to feel colder. I try to come up with a good analogy for this, and the best analogy I have is imagine two buckets. You have two 5-gallon buckets. You have one that's full of water and the other one's empty. And I say I want the empty bucket to be half full of water. What's the only way to do that? Right, you can take the full bucket and you pour half of it out into the empty bucket. You have to take where you have presence of something, so the full bucket of water represents thermal energy, and you have to pour it into the empty bucket, which would represent the absence of thermal energy. If you go back to the beginning of that scenario with a full bucket and an empty bucket, there's no way that you can transfer emptiness of the empty bucket to the full bucket. It's impossible, right? It's laughable, like just trying to imagine. All right, here's the empty bucket. I'm taking half of this empty bucket and putting it into the full bucket. It just doesn't make sense. It's not physically possible, and that's how heat transfer works. It can only flow from where it is to where it isn't. It can't flow from where it isn't to where it is. All right, moving on. So how does heat transfer work? Well, it works in 3 ways. What are those 3 ways? Radiation is the first way. It's the transfer of energy by electromagnetic waves. If you remember way back when we talked about electromagnetic waves, we learned that they're energy waves, right? And they're different from any other kind of wave in that they can travel through vacuum. And this is good because this is how we get energy from the sun. Radiation is how we get energy from the sun, through electromagnetic waves. If you're feeling heat and you're not directly above it and you're not directly touching it, then you're feeling the heat from electromagnetic waves. So if you're standing next to a fire and not in the fire, you feel the heat. Well, you're feeling the heat through electromagnetic waves. You're feeling the heat through radiation. Alright, second type of heat transfer is through convection. This is the transfer of energy by currents. Normally when we're talking about convection, we're only talking about energy transfer through either liquids or through gases. So, through water or through air. Convection currents is how the oceans stay relatively same temperature. It's how the air around us is relatively the same temperature no matter where we go. It's through convection. Hot air rises, cools off, drops down, and you have that up and down cycle. Again, when we're talking about convection, it's usually only talking about through liquids or through gases. And then last type of heat transfer, the one you're probably most familiar with, is through conduction. Conduction is the transfer of energy by touching objects. This is the energy that's transferred through direct touching. So when you put your hand on a hot pan and you burn the crap out of your hand, well, you just burn the crap out of your hand through conduction. Or, if you were to happen to grab a molten hot penny for some reason, that would be burning your finger through conduction. So here's a little example. Fire, heat to the side, you're feeling heat to the side, that's through radiation. The water inside the pan is getting hot, rises, cools off, falls down, that's heat transferred through convection. And the pan handle is starting to heat up and get hot. This is heat transferred through conduction. Alright. Okay. A couple more things to talk about here, and then we'll be done with this first half of this video. There's two types of processes when it comes to transfer of thermal energy, and they're basically opposite of each other. There's exothermic processes. Exothermic is any process that gives off heat. Essentially, the heat transfers from the system to the surroundings. From the system, what this means is where your focus is. In this class, most of the time, the system will be, our focus will be like a chemical reaction. So if a chemical reaction happens and then heat is produced, it heats up the surroundings, the air or something around it, that would be an exothermic process. So if we're doing a reaction and we're monitoring the temperature and the temperature goes up after the reaction has occurred, we would say that that reaction is exothermic because it released heat, the system released heat, and the temperature went up. Exothermic processes, energy is exiting the system. So let's look at an example of an exothermic process. So here, the production of water, hydrogen gas and oxygen gas synthesizing to make water. The hydrogen and oxygen combine to form water, and then energy is released. So this would be, if you were monitoring this with the thermometer, at the end of this reaction, the thermometer would be reading a higher temperature because energy was released. Here's another one that's kind of interesting. Water as a gas turning into water as a liquid. Water as a gas turning into water as a liquid. What is this called? Anybody know? It's called condensation. How do we get gases to turn into liquids? We have to remove energy from them, or in quotations, cool them off. You cool off a gas, you take energy away from those particles start to slow down, and eventually if they slow down enough, it'll turn into a liquid. This is an exothermic process, gas converting or phase changing into a liquid. So the opposite of exothermic would be endothermic, any process in which heat has to be supplied to the system. So in this case, energy is coming from the surroundings to the system. It's being input. Energy is entering the system. So at the end of this process, the energy that you have will be greater than the energy that you started with. Endothermic processes, energy is being input into a system. So again, if we're talking about a chemical reaction here and we're monitoring it with a thermometer, at the end of the chemical reaction, the temperature on that thermometer, the readout on that thermometer should actually go down because that reaction was stealing energy from its surroundings. Not a lot of chemical reactions do this. Most chemical reactions won't cause the temperature to go down, but most chemical reactions require some sort of input energy at the beginning. We'll talk about that, what that means in a little bit. So a lot of exothermic processes, chemical reactions actually have to have a little bit of energy input them in the beginning. But ultimately what we're talking about is the difference overall. So from the beginning to the end, the amount of energy in this system will be greater than it was at the beginning of the process. Energy is being input. So here we have decomposition reaction. Most of the time, decomposition reactions don't just happen on their own. They require some sort of input of energy. So here, mercury oxide plus energy, probably in the form of heat, is decomposing and breaking down into mercury and oxygen. If we were looking at this, at the energy of this compound versus the energy of these two, the energy over here will be higher because energy is being put into this. Energy is being entered into the system. So what about phase changes? What's a phase change that requires energy to be input? This one's pretty straightforward, right? Water as a solid, otherwise known as ice, turning into water as a liquid. So how do we get ice to melt? That's right, we put energy into it. We heat it up. Endothermic versus exothermic. Exothermic occurs with the release of energy. Energy is exiting the system. Endothermic occurs with the input of energy energy is entering the system. So phase changes. You don't really need to know about the pressure side of this. Really, all I'm focusing on is the temperature. And all you really need to know is which ones are considered exothermic, which ones are considered endothermic. So let's go this way. So we're putting energy in, and temperature is increasing. So we're adding energy, going in this direction. So going from a solid to a liquid requires us to add energy. To melt something is an endothermic process. We're adding energy. To cause a liquid to turn into a gas, we have to continue to add energy to it. We're inputting energy. So vaporization is also an endothermic process. Down here is one you may not be familiar with. It's called sublimation. This is when a solid turns directly from a solid to a gas. Sublimation is also an endothermic process. Opposite of these would all be exothermic. Freezing, removing energy from it, is an exothermic process. Condensation, removing energy from a gas to turn it into a liquid. Exothermic, you're taking energy out of the gas for it to turn into a liquid. And down here, deposition, turning a gas directly into a solid, requires the release of energy. So our endothermic, melting, vaporization, sublimation, or exothermic phase changes, freezing, condensation, and deposition. Alright, we're going to stop that video here. We'll come back with another video pretty soon, and we'll talk about these exothermic and endothermic processes. We'll look at these a couple graphs, and then after that we'll look at specific heat. Alright, that's it. See y'all later.